Hello, welcome back to the second part on system design, Instagram, and an implementation with Azure and .NET 8. In this second session, we're going to discuss the different parts of a system design interview. Let's start. The first part is the requirements. These requirements are going to be provided by the interviewer, and we have two types of requirements. We have the functional requirements and the non-functional requirements. As it says here, the functional requirements specify the behavior or functions that a system should perform. It describes what the system should do. And the non-functional requirements, this specifies how the system should behave. Let's take these functional and non-functional requirements provided by the interviewer. So the functional requirements are that the user should be able to upload an image, should be able to like, post, to follow users, and to load a new feed. And as non-functional requirements, we can see that the ones that are more important are the one that the first one and the second one. That is, it should be able to handle 10 million daily active users. And the second one is that it should be able to load the new feed really quick with a low latency. We also have extra information that is going to be used in the later steps. For example, that the maximum allowed image is 10 megabytes, that it should be able to handle at least 100,000 concurrent uploads, that the user can only upload 10 images per day, it should handle at least 1 million concurrent likes, handle at least 1 billion registered users, and users should be able to follow at least 1,000 other users. So these requirements are going to be utilized to design our system. So let's go to the second part, that is capacity estimation. In the capacity estimation section, we use this part to predict the resources required by a system based on the non-functional requirements. The capacity estimation is important because it will affect how the system will be designed to meet the non-functional requirements expectations. So we have here 4 different parts that is on the capacity estimation, and I'm going to show you this a little bit bigger. And we can see that we are calculating the traffic, the storage, the bandwidth, and the memory. So I use this small table to do my calculations, so you can use it too to do the calculations. And let's go really quick over each one. So the traffic. We know, based on the non-functional requirements, that we are going to have 10 million daily active users. So how we transform these 10 million daily active users into traffic? Well, first we need to convert into requests. And to convert into requests, we need to know how the user will be typically using the application. It means that it is going to be reading or writing. So in this case, we are assuming that it will be 10 times more reading than writing. And based on that, we can now do some calculations. For example, we know that we have 10 million daily active users, and only 10% is going to be uploading images. Each one is going to upload 10 images, and that gave us 10 million upload requests. And we do the same calculations for the reading. And then we transform that calculation in that it's in days into seconds. And that gave us 100 writing requests per second and 1,000 reading requests per second. In the second part, we have storage, and we know that we have 10 million upload requests per day. We know that because we calculate this here. And we also have an average size image of 5 megabytes. We do multiplication, and that gives us 50 terabytes. Are we gonna have also a retention period? In this case, we have 10 years. So we do the calculation here, and As you can see here, we are gonna round the number. In this case, how many days has 10 years? Well, 3,650, and we just round that number to 4,000 just because it's easier to do calculations, and that's fine in a capacity estimation. And we also, once we have the multiplication, we know that we are gonna have 200 petabytes. We also some additional 50 petabytes just to say that we're gonna have different resolutions per each image, and are gonna have replication. Of course, we're gonna have 3 backups, so we just multiply the 3 by the 2 petabytes, and also for the 50 petabytes, we just sum that, and we know that we're gonna have 750 petabytes in the 10 years that our system is gonna be running. Next, we go to the bandwidth. We know that we have 100 requests per second for the incoming data. In the writing request and the reading request, we have 1000. We did that calculation here, and we just need to multiply that for the size of the image, and we know that we're gonna have 500 megabytes per second for writing requests, and for reading we're gonna have 100 gigabytes per second. And the last part that is the most important one for Instagram. And just as a comment, I first did the design and then I did this calculation because I didn't know what I was gonna store. So I'm just gonna explain this, and it will make sense once we go to the part of the design. So in this case, I'm gonna store an array of GUIDs, and I know each GUID has a size of 16 bytes. So I'm thinking about to store per each user 100 GUIDs. So I do the small calculation, 100 by 16 bytes, and that gives me 1.6 kilobytes. And as I'm gonna have 10 million active users, I multiply 1.6 kilobytes by the users, and that gives me a size of 16 gigabytes that my server has to have. And with this, we finish the part of capacity estimation. The next session is the logical diagram. So let's go to the next part. Let's continue with the design of the logical diagram. How do I end up designing the system like this? Well, I didn't start like this. I first started small, so let's go small. Based on this monolithic architecture, you can see that we have all the functional requirements in this side. The user is capable to like, follow, create posts, and get new feeds. But what is the issue with this monolithic architecture? Well, the issue is that we're gonna have 100 requests per second writing and 1000 requests per second just to load the new feed for each user. Given the amount of requests, it will still give a heavy load into the database. That will cause performance issues and data degradation, and most probably it will not accomplish what it was asked on the non-functional requirements. That was being able to have a low latency load in the new feed and being able to handle 10 million daily active users. Well, given the problematic of the monolithic applications, we need to find a solution. And the solution is a microservice architecture. The microservice architecture improves scalability, and that will solve the non-functional requirement that is handle 10 million daily active users. How a microservice architecture improves scalability? Well, it does it by breaking the monolithic application into different modules, and those modules can grow and scale horizontally. And that's how microservice architecture managed to improve the scalability. Well, yes, microservice architecture will solve the issue of handling 10 million daily active users, but that is not going to solve the high latency on the newsfeed. And how do we fix the high latency on the newsfeed? Well, we're going to solve that using a pattern that is called fan out pattern. Before going into how the fan out pattern solves the issue on the low latency news feed, let's review the diagram and see how I end up breaking the monolithic application into the different services. So first of all, you can see that the clients are not reaching anymore directly the server. Instead of that, it is reaching a load balancer. A load balancer will provide security, availability, and scalability. It provides scalability by scaling horizontally, and it also provides availability by having multiple servers acting as a load balancer. Then we have our different services that were breakdown from the monolithic application. So first, we have the like service that is going to be in charge of processing all the likes and unlikes. We have the friend service that is going to be in charge of processing the follow and unfollow. And we have the post service that is going to be in charge only to create the posts. And we have also the feed service that is going to be in charge of loading the new feed for the users. We also have additional services. For example, we have the rank service, and the rank service contains the necessary logic based on the likes and user follows to determine what users are going to see the shared post. We also have the post processor, and the post processor is going to be in charge of pre-compute the user's timeline. So that's how I end up breaking the monolithic application into our different services. The other services. Let's start with Cosmos DB. Cosmos DB was chosen here because it's a NoSQL database. And NoSQL databases are well known because they allow you to scale horizontally. This type of scaling lets you handle an increased workload by distributing the data across multiple partitions and server. Cosmos DB also provides global distribution by displaying different instances of Cosmos DB around the globe. It also has availability with 5 nines, which means that it will have around 5 minutes downtime average over the year. It also provides high throughput, and if you choose the partition key correctly, it will provide you unlimited storage. We also choose blob storage. Blob storage is a special storage in Azure that allows you to save any type of files. That includes images. That's why we choose the blob storage. Connected to the blob storage, we have the CDN, that is the Content Delivery Network. The Content Delivery Network provides static and dynamic content at ultra-fast speeds by decreasing the distance between where the content is and the final user. Content Delivery Networks works by also distributing the servers around the globe. The next service is the Redis server, and in the Redis server we're going to pre-compute the user timelines. Redis, it will increase data throughput by over 800%, and it will increase latency performance by 1000%. This is all compared to an SQL database. It is a great way to efficiently scale applications. And the last service that we're going to be reviewing this time is going to be the Azure Service Bus. In this case, the Azure Service Bus is a message broker. And the message broker in a microservice architecture helps by decoupling the applications by acting as an intermediary between the different systems, allowing them to communicate without being directly connected or dependent on each other. This decoupling enables applications to function independently. This improves the scalability, the flexibility, and fault tolerance. Message broker also enables asynchronous communication between the different services. This means that the producer, the service who is gonna create the initial event, doesn't need to wait for the consumer to be ready or online to receive the message. The other advantage, as was mentioned before, is that they enable also loose coupling. By using the message broker, the applications are loosely coupled, meaning that they don't have to know about each other's existence, protocols, or implementation details. The producer only knows how to send the message to the broker, and the consumer knows how to read those messages from it. This abstraction allows developers to change, update, or even replace components of the system without affecting the rest. So let's finalize the review of the logical diagram by going through the workflows. So let's start with the like and unlike, and also the follow and unfollow. Once the user likes or follow a new user, you can see that they both reaches their own service. These services pretty much act the same. Both will create an event that will be triggered to the Azure Service Bus. Then we have the rank service. The rank service will process those events. Inside the rank service, it will contain a logic that will determine what users are going to see the shared post. The next workflow that I want to show you is the one that follows the fan out pattern. So let's first start by creating the post. Creating the post will reach their post service. The first step that is gonna happen here is that the post service is gonna save the information into the Cosmos DB. After it saves the information into the Cosmos DB, it will also store the image in the blob storage. The blob storage will distribute the image into the CDN. Then the post service will execute an event called post ready. This event will contain the information from the post that was created. This event will be sent to the post processor. The first step that the post processor is gonna do is to actually get the list of friends that user is gonna share the post. That's why it is important to have that information in the rank service. Once it knows to what users this post is gonna be shared, the post processor will store that information in the Redis server. Remember that the Redis server stores the information as a key value. So in this case, you can see in this small table that we have the user ID, and that user ID contains all the post IDs that user should see. And by having the pre-computed timelines will allow us to fulfill the requirement of low latency new feed. So as a final step, we need to actually load the new feed. And remember, we need to do this with a low latency. And for that, we are using a fan out pattern. We already fulfilled the first part. The first part is to have a pre-computed user's timelines, and we got that in the post processor. Okay, so the first step is that the user will try to load their news feed, and for that it will send the user ID to the feed service. The first step that the feed service is gonna do is to send that user ID to the post processor to get all those post ID that belongs to that user. As it is using a Redis cache, it is super fast, and it will retrieve that information to the feed service. And once the feed service has all those post IDs, it will send that list into the post service. The post service will retrieve the information from those post IDs using or calling their Cosmos DB. Once the post service gets information from the Cosmos DB, it will retrieve the information to the feed service, and the feed service will retrieve the information to the client. Once the clients had the information from the post, it will reach the CDN to load those images as fast as it can. Remember that the CDNs deliver static content in an ultra fast speed. And this is how our system fulfills all of it. In the next section, we're gonna design our tables in our database. Remember that we are choosing a NoSQL database, and we're choosing a NoSQL database because it comes with features that we need to fulfill the requirements, as it is the horizontal scalability, availability, global distribution. Once we know that, it is also important to know that NoSQL databases scale really good horizontally, but it comes with a price. The price is that you need to pick up a primary key in each container. A container has an equivalent to a table in SQL database. And that partition key will determine where the information is going to be stored logically inside the servers. It also knows exactly where to pick up the information based on that partition key. And that comes with a price. We don't have relationship within the containers inside a NoSQL database. So based on that, we need to design our tables using the normalized data. That means that we are gonna have duplicated data, but that's okay in a NoSQL database. So once we know that, we have to choose or to pick up the partition key very careful. Why? Because choosing the correct partition key will allow us to have limited storage. So how do we choose the correct partition key on our containers? In order to choose the correct partition key for each container, we need to know against what data we're gonna be querying our database. So let me give you an example. The rank service. The rank service has a container, and what is gonna be querying against? It is gonna be querying against the user ID. We need to get the list of friends given the user ID. So the most common sense is that if we are gonna be querying against the user ID, well, the user ID should be the partition key. So in the rank container, we have the partition key as the user ID. For the friend service, we are gonna be querying against the user ID. So the user ID is a partition key. Also, although it is not illustrated here, the like service will also contain a Cosmos DB connection that has a container, and as we're gonna be querying against the post ID, the post ID is the one that is gonna be the partition key. And finally, the post service. The post service, we can see that we're gonna be querying against the post IDs. So if we wanna be querying against the post IDs, the post ID is gonna be the one who is the partition key. Remember that we don't have joins in the NoSQL database, so we need to design our containers with the normalized data. That means that we are gonna have duplicated data, but that's okay inside the context of a NoSQL databases. Finally, as a last step in a NoSQL database as Cosmos DB, it is okay to join those tables who has the same partition key. And just as an example, we join the friend and the rank container together, and we created this follow container. And the follow containers has the same information as these two tables, plus this row that is called follow type, that will distinguish between a friend and a rank. And the final step that I want to show you here is this diagram. This diagram is not necessary for you to create it, but I did it because it's easier for me to understand how my services are connected to which topics and to which subscriptions. And this is easy for me to solve issues once I am working with the services and the events. So for example, this is the Azure Service Bus, and in here we have the topics that are inside the service bus. So we have the follow topic, the post topic, and the like topic. And each topic has its own subscriptions, these subscriptions. And what are the services who are subscribed to those subscriptions? Well, we have them here. For example, the post service is listening to the events that the like topic is creating. And also the rank service is doing the same. And for the follow topic, who is the one who is creating the events? Well, the friend service. And who is the service who is subscribed to those events? Well, the rank service through the rank service subscription. And that's how I managed to understand how services are connected to what and which services are creating which events. And as a final step, we're going to review this new diagram. And as you can see, it represents the same diagram that we designed before, but using some Azure services. The API management will be represented as the load balancer. You can see that we have also our services already as Docker images pointing to the Cosmos DB. And we also have the Azure Service Bus, and this will be distributing our events. We have also the Azure Redis Cache, that is an instance of the Azure Redis running in our Azure cloud. We have also the blob storage, where we're gonna store all of images, and we have also the CDN, that is the Content Delivery Network, that is gonna help us to speed up the load of the images in the client applications. I'm not gonna show how the Azure DevOps works because I am limited on what I can do on my new account. But if you wanna know more about this, I already have some tutorials in my YouTube channel where I explain how to create the Azure repositories, how to create the Azure pipelines, how to run the Azure container registry, and also how to create the continuous delivery pipelines and deploy as the new application as soon as we have a new image in the Azure container registry. And all of that is here in my YouTube channel. So let's start by reviewing some of the services that I have deployed on my Azure account. So the most important one are the Cosmos DB, and as you remember, we have these 4 containers: the post, the light, the friend, and the rank. So let me show you really quick that part. And as you can see here, I am already logged in into my Azure Cosmos DB account, and if you click on the Data Explorer, you can see that I created a database called Instagram DB, and inside this Instagram DB we have these 4 containers that will have our data. The data that is inside these containers are called items, and these items are just JSON objects. And as you can see, for example, we have here 3 items, and each one contains this JSON string. One important thing, for example, in this, let me show you the rank items. We have here a user ID and their friends, which it will be sending their posts. And these friends, as you can see, it is just a string separated by a comma. And let me show you really quick how this works in code. Let me display. And in my code, I have these 4 services: the feed service, friend service, like service, post service, and also I have also here the post processor and the run service. And let's go into the run service, and let me show you that we need to specify some things in the DB context. In the DB context, it's really important that on the modeling creating method, we need to specify the container name and the partition key. This is really important. And just for this situation, I have a conversion. Why? Because the model rank, you can see that I have a friends or a list of friends here. And as I mentioned before, the friends is not a list, it's just a string separated by a comma. So what I'm doing here is doing a conversion. So when it loads the ranks here, it will convert that string into a list. Let me show you also the post service, for example, the DB context. The DB context, I specify the container name and the partition key. This will allow to actually query or Cosmos DB database. Well, let's go now to the next service. and that next service is gonna be um, the Azure Service Bus. In the Azure Service Bus, remember, we have three topics: the follow topic, like topics, and post topic. And inside each topic, we have subscriptions. And those subscriptions, let me show you really quick that Azure Service Bus. Let me go to home. Here I have my service bus, and inside my service bus, you can create new topics if you wish. And once you create your topics, you just click here on topics, and you're gonna see the different topics you have created. And in here you can also see the subscription number that each one of the topics has. Let's go, for example, to the like topic, and we can see here below that it has two subscriptions: the post subscription and the rank service subscription. You can see the status, the message account, the active messages, and some other details of each subscription. If you want to create a new subscription, just need to click here, create subscription, and you will have to define some values for this subscription. And now let me show you how this works on the side of the .NET Core. So for the part of .NET Core, first you need to have some dependencies. For example, you need to add this Azure Messaging Service Bus, and you also have to I have some settings, like for example, here in my application settings, I have this each consumer, the one that is gonna actually read the event. I have different settings for each one. For example, it says to which topic it is subscribed and the subscription. I also, in this case, I created the connection string here. I know it's not a good practice, but for this example, I just put it here. And one thing is that each consumer is gonna be inside one background service, and this background service is extending from the iHost service. And each host service, for example, you can see here that I have this, in this case, let me see, this is a post service. So if we go to the post service, we can see that the post service will create some events called post created, but it is also subscribed to the post service subscription. And let's go back. So I have only one background service, and you can see that what it will do is that it will start this topic consumer task service, and this task service what it will do is just to be in charge of reading the event, and each event will have a type, and depending on that type, it will get a strategy that will be in charge of processing that type of event. If it finds that strategy, in this case the strategy is going to be, for example, the like created event, because it is not the same when it receives a like created event and when it receives an unlike created event. So depending on each type, it will try to manage or to have their own logic inside the strategies. And in this case, let's suppose that it receives a like created event. It will retrieve this strategy called like created event, and this has the logic that will process the like created event. that in this case is gonna deserialize the type of light created and will send um, well, in this case it is gonna process first the event, sending that into our light created processor service that most probably will store the information into the database. And well, I think that this is the most important thing about it. The one that is gonna be publishing the events is actually using this class common called event bus, and this is in charge of actually publishing the events into the Azure Service Bus. Now let's go to the next service, and we have the Azure Redis cache. And for this one, I also have an instance created in Azure. And in here, let's go home. We have here our Azure Redis cache, and inside this one we have after creating the instance of the Azure cache, we have here some authentication values that are going to allow us to connect to the database, and also I have this Redis Insight application that will allow me to query the database. And as you can see, I already have some values for this user ID, which contain the posts that will display to this user. Also, it's important to show you that in the code, the post processor is the one that have access to the Redis. So we have here also a library called Stack Exchange Redis that is used to connect to the Redis server. And the way I created the connection, it was actually in the program by loading the connection string and creating a singleton using the connection multiplexer. Then we inject this into a repository, and this repository has this iDatabase that will contain the connection to our database. And then we have several methods that will be executed to retrieve or store new data into our Redis cache server. And I think the most important method here is the one that is updating the posts in the Azure Redis cache, and this is the method that is doing the job of updating our list of user and posts. And I think this is the most important part about this service. Also, let me review again. The next one is gonna be the blob storage and the CDN. So let's go back again into our Azure's account, and let's review the blob storage. Let's go to blob storage, and I have here my blob storage, and I also have my CDN created on my blob storage. So in the blob storage, we can see here in the part of security and networking, we have our front door and CDN, and you can click here and create your own. In this case, I created a front door, and this front door is acting like a CDN. And as you can see, we have here it gave us a host name that is gonna be used to go directly to the images using the CDN instead of querying directly to the blob storage. And inside the blob storage, we have a container. And inside the container, you can see that I have here a container. And inside this container, I have all the images that are stored from the post of the users. And let me show you how do I connect to the blob storage using, it was the post service. Inside the post service, I have to also add a new NuGet package called Azure Storage Blobs. And if I remember well, I have this in a service. Here I have the method save image to the blob storage. As you can see, it is a type of iForm file, and this is the one that creates the image and stores the information into the cloud. It also, into the blob storage inside the Azure cloud, and we also generate some, this is a token to be able to have security on our images. And also we return the URL of that image as a result in our, once we store the information on our blob storage. And this image will contain this token that is gonna be valid for a certain time of a period of time that I don't remember that I configured, but I think it's like 1 day, I think. And well, this automatically will return also the URL from the CDN, making or being able to load the images faster. And finally, I think these are all the storage. Well, I think that's it. I'm gonna do a really quick demo. I'm still running the services locally, but those services, as you can see, they are running on my on Docker images. And the first thing that I'm gonna do is that I'm gonna create some custom friends by calling the rank API that is called rank. And what I'm gonna do here is that I'm gonna say which friends can see other friends' posts. Like for example, this post, you can see that this is 1, this is 2, 3, and 4. So the first user has these 3 friends, which means that if user 1 posts something, user 2, 3, and 4 can see the image. And here, if the user 2 posts something, user 3 should be able to see this. And this is the test that we're gonna execute today. Like for example, I'm first gonna delete everything in the rank. And the rank service, let me check really quick, because the rank service is running on port 5006. Okay, so let me execute this again. 5006, yes, let me delete everything. So now if we go to our Cosmos DB, we should not see anything inside. Let's go to Data Explorer. Um, so while it is loading, I'm gonna explain what I already explained based on these values, but with some images. So I have the same representation here below. So this is user 1 called alpha, 2 beta, 3 Charles, and 4 delta. So remember, alpha have 3 friends, and if he posts something, these 3 friends should be able to see their posts. And if user 2 posts something, user 3 should be able to see it, and so on. But for our test, we're gonna execute 2 posts from alpha and from beta, and we should be able to see that only user 3 should see 2 posts from beta and from alpha, and these 3 guys should see only posts from alpha. Let me see if we can already see or rank container. Let's see some items, and it doesn't contain anything. So let's do the job and let's execute this friend list that is gonna be stored in the rank service. So it is done already. Let's update this, and we can see that the information is stored in the rank container. So let's start by deleting all the posts also. Let me delete all the posts. Okay, we didn't have any posts, and let me execute this. We can delete. Okay, I wanted to show you this part, but I cannot delete from this. The next part is actually I'm gonna create some posts, but I'm gonna use the application that I created using React, and I'm gonna simulate the login and that I'm logging as user 1, and let me do this a little bit smaller so you can see the button, and it's gonna create a new post as user 1, and and I'm gonna create a post. Let me log out, and I'm gonna log in as user 2, and user 2 is able to see the alpha posts, and I also can do some likes. I can log out, I can log in as user 3. I'm gonna log in as user 3, and as you can see, I'm able to see alpha's post, and I can see that it also has a like. Let me log out again, and let me do the second part that I mentioned, that is login as user 2, create a post, and let me choose a new image, for example forest, and the forest. Let me create the post, and let me log out again, and remember, only user 3 should be able to see both posts. So let me log in as user 3, and user 3 is able to see both posts from user alpha and from user beta. And now I'm gonna log in as, for example, user 1. He should not be able to see any posts because he doesn't have friends. And let me log in as user 4, for example. He should be able only to see user 1. And he can click here also in likes. I'm gonna log in again as user 3. Should be able to see 2 likes now in the alpha post. Well, that's it. It has been a really big project for me, and if you have any questions, please just send me a message. I am gonna be uploading all the code into my Git account that is gonna be on each of the YouTube videos. And that's it. Thank you very much for watching.